Hello everybody, this is a quick video on mutual exclusion and critical sections, and how we're going to provide that mutual exclusion to critical sections is going to be with explicit and implicit locks. To review from previous videos, we talked about data races and race conditions. A data race is when more than one task is accessing the same data and at least one of them is mutating it or writing that data. And a race condition is when the correctness depends on how that whole thing plays out. Neither of these two are a subset of each other, but we did talk about one example, which we're going to use again today, which is, this shared mutable data, which is a family's bank account balance. One member of the family is reading, modifying, and writing that data, and while at the same time, someone else, another member of the family, is reading, modifying, and writing that data. We had this data race program, which is gets the Mr. Yuck symbol because the son is reading, subtracting, and writing at the same time. The dad is reading, modifying by adding, and writing that data. And nothing is protecting it from happening. These two tasks can run in parallel. We have this data race. And so the program will produce different answers. So like if I come over here to this program and I run it really quickly, this program will work sometimes. As we can see right here, that one worked. But if I run it again, it will throw an error because the dad read 500, the son read 500. They both operated as if that was correct. Dad wrote out 600 after adding $100, and the son wrote out 300. Guess what is not $400, this answer. And so that is a race condition that that happens because of a data race. And so we want to prevent that. And so how we can prevent that is by providing mutual exclusion. We can protect these two sections of code when they're protected, that we call critical sections, such that only one can happen at a time. So there's a way to do this explicitly. There's an interface lock. I've provided a link here. It's provided in Java. It goes all the way back to JDK 1.5. It has methods lock and unlock. Lock acquires the lock, and when you have acquired a lock and you hold that lock and you're the owner of that lock, anyone else who tries to acquire that same lock will wait for you to unlock it. And so just really quickly, this is a lock is an interface, and there's a class that implements it called reentrant lock. And reentrant lock just means that once a thread or a task we've talked about in this class, thread is a more heavyweight version of that, of just code that can run in parallel with each other. You can recall lock if you want. So if you hold the lock, you can call lock again and won't block. If someone else holds the lock, you'll wait. But reentrant lock just makes it so if the same thread calls it again, it'll just keep track of that in account, but it won't block them. It's hard to imagine how you would want different behavior than to be like, all right, I have this lock, I've asked for it again. Just keep track of the fact that I asked for it twice, rather than block me, because I'm going to have to unlock myself eventually, so it would be disastrous if it wasn't a reentrant lock. And so how you use these things is you can create a new reentrant lock here at the very beginning of our program, and then what I'm going to do is I'm going to protect both of my critical sections of code by calling the lock before I do all of the work that is necessary. Now note, Marvel at Art for the son and Dad Strive to Work is not part of this critical section where we're reading and writing this same data. And so we don't have to protect that with a lock, so those two can run in parallel without a problem. Once they both acquire this lock, the same lock, now the lock will make it so only one can acquire this lock at a time. And so let's say the son gets it first. They will acquire that lock. They will then do their work. Say while they're halfway through it, contemplating where to hang the art, the dad comes along and tries to acquire that lock. It will wait until the son has unlocked it. Alternatively, if the dad gets it first, the son will wait. This is a very nice and powerful bit of ways to keep things thread safe or prevent yourself from having a data race. So I have this version right here, and when I run it, it's going to come up with the right answer all the time. Right now, the dad won, so the dad gets to read and write first, but the son waits for that to complete. So if I run it again, the son got it first this time. read 500, wrote 300, the dad reads 300, the dad writes 400. If I run it again, we get the same behavior. Son won that time. We run it again, see if we can go back. Dad won this time. Again, but we're okay. We end up with this, what I would refer to as a correct answer at the end, which is $400. And so this mutual exclusion is a very powerful and useful tool. If we come back over here, you'll note there's this bonus thing that I put in here, which is called try finally. Try finally is a very useful feature. The finally block in a try finally, you can think about it when you open. A lot of you should probably know that when you open a file, you should always close it. And so it's good to wrap that in a try finally. Open the file, do whatever processing you need to do, and then when it's done, close it. This is just little pseudocode. I have like actual code over here with the braces and everything. And then no matter what, if the try block completes unremarkably, it just finishes normally, you return within that try block, an exception is thrown. So somebody throws an IO exception or whatever you want here, you name it, finally will run. And so that's useful for things like files, connections to databases that have to be cleaned up. And something that always has to be cleaned up is whenever you acquire a lock like this. The last thing you want to do is acquire a lock, throw an exception in here or return or whatever, and forget to unlock it. And so even if you could prove and know that this will never throw an exception or never return, it's good to do it in a try finally block. Just for no other reason to indicate to your reader, the person who's reading your code, like this must happen. And even if you could prove it, you put it in there just in case somebody changed it. And so that's one thing. That's explicit locks. They work. They're fantastic. And what I'm going to talk about next is implicit locks with this keyword in Java called synchronize. You can synchronize a method. When you synchronize a method, if it's static, it's on the class itself. Otherwise, it's on this instance or a block. And I have some links here to sort of the standard Java documentation on this matter. But what it does is it has an internal lock, if you will, an internal monitor that provides the mutual exclusion. This goes way back. It actually predates locks in Java from day one. And you should use this whenever you can. It's a little bit simpler and it's a little bit faster. Not too much, not significantly, but it's a little bit faster, but it's also simpler. This, if you look back here, I have this lock where I create it and I call lock and I have to do the try finally and I unlock it. What synchronize does is it allows you to use any object you want, so not a primitive int, but any object like an array, in this case, of the balances, and synchronize on it. What that will do is acquire the lock for that and hold it until the block ends. So it's sort of the same thing, but cleaner. And so you should always use this. Sometimes you get a little bit fancier with your locks, and this will be a little bit awkward or impossible to do. I guess maybe not impossible, but just cleaner to do it this way. We're also going to get fancy with the spices later when we do try locking and all sorts of other stuff. So explicit locks have their use, but when you can, just use synchronized. It works well. And so let me do a quick, first of all, this is nice. Both of these are nice. We always get one of these two cases where the son reads to and writes to completion before the dad reads and writes, or the other way around. We never get one of these interleavings that causes a bad program. So let me just show off the implicit lock version. Let me see if I've got it right here. This one looks very similar to the other one. It just has the synchronized on balances in both cases. And so if I run this, and again, I can run this as many times as I want, it will always, the order might be different. See, dad was first to go this time, and son was second to go that time. If I run it again, dad was first again. Run it again, dad was first again. Let's just keep running this until we get the son to go first. There goes the son. No matter what, the answer is always 400 at the end, which is correct, so we're happy about that. And so both solutions work and work well. And this is the key. This is what we're trying to do. We're trying to prevent incorrect behavior. We want it to always come out with the same answer, 400, and so we've achieved that. One quick note is all the critical sections, in this case there are two of them, so both of them, accessing a particular shared mutable data, piece of mutable data must acquire the same lock, whether it's explicit or implicit. I have versions of this really quickly, but here I've made two different reentrant locks. One to protect that I intend to protect the balance, and another is supposed to be for something else. The son acquires the lock that perhaps was reasonable to acquire, and the dad acquires some other lock. This is a data race. This doesn't protect anything. These two things are accessing this piece of data, and they are acquiring different locks, which essentially both of them are allowed to proceed as if you didn't have anything. It's just got maybe a little bit more overhead. Let me show the other one too before I move on and show them in the thing. The same thing can happen with the synchronized block. If this guy synchronizes on the array and the other one synchronizes on himself, like dad or son, or makes a string called Fred or whatever, they are synchronized on the wrong thing. Now, it doesn't have to be balances. Well, let me show this off in the code here. This is the, let me show off the explicit lock one first. That has a data race here. There's two different locks. We're going to acquire the wrong one. And sometimes it'll work, sometimes it'll fail. Let's run it a couple of times until we can get it to throw an exception. There it is. Because this one is preventing any other threads or tasks to get in here that are acquiring the same lock. But Chucklehead Jones down here is acquiring on a different lock. They're both mutating the same data, and so that's a problem. This is the exact same situation here with the synchronized block. The son is synchronizing on balances before it goes. Dad is doing this. Now, to be very, very clear, this one will also fail. If I were to change this, it's not that balances is somehow special. This is just something where first of all, if I change this to balances like it should be, it goes well. All right, it'll be correct every time. Also, other stuff because we get the same object. If we just arbitrarily chose to always synchronize on the son, right? As long as everybody goes on the same lock, right? Whether it's implicit or explicit. Oh, I got an S now in here. Yeah. Save that and run it again. This will be correct because they're both. Let me just make this a little bit bigger here. They're both synchronizing on the same object. So it's nothing like, as long as you do the same thing, I can make some string, Fred. And I can call it George. I can do whatever I want, right? And if everybody who's accessing the same shared mutable data just always does the right thing, right? Like there's no more yuck because I'm doing the same thing. Now, it might be kind of ridiculous to call you variable Fred or whatever, but as long as everybody does the same thing, again, the same thing is the case with an explicit lock. So back here, we definitely do not do these, decide what's going wrong. The other thing that's critical to note is neither one of these are safe. This guy can crash or this guy can crash. Just because we all agree, if 9 out of 10 people are synchronizing on balances and someone else is doing the wrong object, like everybody's not safe. So all of the tasks that are mutating the same or accessing the same data with at least one of them writing need to be on the same object. And so that's why we go back to these two, which are correct, where we have a lock that protects both of them. That's an explicit lock. And here we are synchronizing on the same object. And so with that, hopefully you'll be able to use mutual exclusion to take when you're mutating shared data and make it thread safe.